Hi, thanks for joining me. Today I'm going to be proving that there are infinitely many primes, and of course it's going to be a non-standard proof. Let's get stuck in. Okay, so the first thing we're going to do is take an arbitrary positive integer m and consider this expression here. It's the product of 1 over 1 minus 1 over p, where p are the primes less than or equal to m. Now this thing here, if we just have a stare at what we're kind of taking the product of, this may remind you of the formula for a geometric series. So if we had 1 plus r squared and plus r cubed and so on, this thing here equals 1 over 1 minus r, and that's provided that r is a complex number with magnitude strictly less than 1. And in fact, we don't need to worry about complex numbers in this video. We're simply working with reals, so that's fine. But obviously here, 1 over p, because p is a prime number, p must be at least 2. So 1 over p is going to be some number between 0 and a half. So certainly it's going to have magnitude less than 1. So we can apply this formula here. So we can write this here now. Well, we still have the product over p prime being less than or equal to m. But now instead of 1 over 1 minus 1 over p, we can write this as 1 plus 1 over p plus 1 over p squared plus 1 over p cubed, and so on off to infinity like so. Okay, so we have that this guy here is the same as this guy here. But now we're going to suppose that m is a large positive integer, and that's fine because what we'll see at the end is we're going to take m going to infinity. Because what we do now is we look at this guy here and say, well, this thing here is equal to, let's just write out the first few terms and the last term as well. So when p is our smallest prime number, so p equals 2, we have 1 plus a half squared, and so on. When p equals 3, 1 plus a third squared, and so on. And then this kind of product thing continues until our last prime, which is less than or equal to m. Let's just call that p tilde. And of course, p tilde will depend on what m is. So 1 plus 1 over p tilde plus 1 over p tilde squared, and so on off to infinity like that. But now I claim that this guy here is bigger than or equal to the sum from n equals 1 to m of 1 over n. So I claim that this kind of product here is bigger than or equal to this guy here. Now, why is this true? Well, I claim that for any n in this range here, 1 over n is going to be somewhere in this product here. Now, why is that true? Well, take any number n between 1 and m. So we're going to have n being between 1 and m. Then n is going to have some prime factorization. We don't know what it is, but we know that all those primes must kind of come from this guy here. Because n is less than or equal to m, if p is a prime that divides n, then p must be less than or equal to n, and thus p must be less than or equal to m. So p must be kind of one of these primes here, 2, 3, 5, all the way up to p tilde. So one of those primes there, or those are the only primes that will appear in the prime factorization of n. So we can write n in the form 2 to the alpha 1, 3 to the alpha 2, and so on, all the way down to p tilde to the alpha, I don't know, alpha tilde, let's say. Okay, so it's just some product of these primes here. But then notice that we're only considering the reciprocal of n. So that's 1 over n then is just 1 over 2 to the alpha 1, 1 over 3 to the alpha 2. Okay, and so on all the way down to 1 over p tilde to the alpha tilde, like so. But notice that if 1 over n is this guy here, well, we're just going to take the alpha 1th term in this sequence here. So let's suppose alpha 1 is just 2 for now. So we're going to take this term here. And then alpha 2 suppose is 1. So then we're going to take this term here. And so on. And let's say alpha tilde is 0. So that corresponds to this term here. 1 over p tilde to the 0 is just 1. And what we're going to do is just multiply these terms together. And so on. And notice kind of when we expand these brackets here, this guy here is just going to give us this thing here, which we know is 1 over n. So that means kind of in this weird looking product here, we have all of the 1 over n's. And notice that there's not going to be any sort of double counting or anything like this, because each positive integer has a unique prime factorization. So we're going to have all the 1 over n's appearing in this sum here, but notice we're also going to have a bunch of other junk as well, but all that junk is non-negative. We might have a, 1 over 2 to the 582, 1 over 3 to the 580, and then 1 over p tilde to the 7064. I don't know, but we're going to have a bunch of non-negative stuff here as well on the top, which isn't in our summation here, and that's why this thing here is bigger than or equal to this thing here. So what we've shown is that the product of the primes, for the primes p being less than or equal to m of 1 over 1 minus 1 over p, is bigger than or equal to this guy here. But we know this thing here is just a harmonic sum, and this, as we take m going to infinity, this thing here is going to go to infinity as well. So as m goes to infinity, so if you've not seen that before, that's simply the harmonic series diverges. I made a few videos of those proving that result. I'll leave links to those in the description. But we have this thing here. Now remember, our job is to prove that there are infinitely many primes. So we're going to do that by contradiction. Now suppose for contradiction that there were only finitely many primes. Well, then that means that this product here is only ever going to be a finite number. Because if there are finitely many primes, then we're only doing the product of finitely many things, so we're going to get a finite number. But that holds for any m, so even if we take m to infinity, this thing here is just going to be some finite number. But that contradicts the fact that it's bigger than or equal to something that tends to infinity, because you can't have something being finite all the time, but then being bigger than or equal to infinity. So that's where we arrive at our contradiction, hence there must be infinitely many primes, and that proves the result we wanted to. I hope that this video has all made sense, and I hope you've enjoyed it as well. Thanks for watching, I'll catch you in the next one. Have a great day.